Hello, everyone. For those who don't know me, I'm Pablo. I'm from UWS, and thank you very much for you all to come here at 9:30 to listen to me like an hour or so. And I'm here to present this kind of workshop or training about the network self-protection loop that is related to the components that we have in UWS and we are providing for the Work Package stream. And first of all, I'd like you to excuse me because in the very beginning there were like 3 different trainings, one for each component. But I thought that in this part of the project, it makes more sense if we talk about the entire loop that the 3 components, that the integration of the 3 components are doing instead of the features of each of the components. So I will be focusing on what the integration of the 3 components are contributing to the project and how do they work together and so on. So for today's agenda, I don't know why. Okay. For today's agenda, I don't know if you can all see well the agenda, but we will start talking about the motivation that we had to start developing these tools or these components. What problems did we discover that there are in the literature and we want to solve as contributions, and what is to be done with the components in the ARCADIAN-IoT framework. Also, I think that this is a very common question, and it's what is a loop? Because I think most of us have been going to the meetings, regular meetings in ARCADIAN, and always people from UWS have been talking about the network self-protection loop, loop. And sometimes we say, okay, so what is a loop? I will explain what we consider that is a loop and what are the main features that those loops should cover, and how we cover those features in our network self-protection loop that are gonna be inside the ARCADIAN-IoT framework. Then we will go deep in the technical aspects of the architecture of the 3 components and the integration of them 3. Also, with how the communication between themselves work, and finally we will work for some real cases scenario that we already presented, for instance, in the demo we did in the previous review. We will see it more in depth, and then we will talk also finally about the contributions. So if you allow me, I will continue talking and we will go for the motivation. So we are focusing on the network side of the ARCADIAN-IoT framework, and we started thinking about how the network intrusion detection system usually work. Here we have a very a picture that depicts how a regular network IDS usually work for a company, for instance, that has a network and wants to protect at least or at least to detect if there are some threats or attacks incoming to our network. For instance, we have here where we can access from the internet to the company premises, and we have after the first router a switch that usually mirrors the traffic that's incoming to our premises, and it's mirroring to a sensor. That sensor is the one in charge of detecting if there's a threat incoming or no. And basically, the security administrators, they are using different ideas, consoles, and tools to monitor and to act in case of a threat detected. But here, there are few problems. Well, few problems or few gaps that should be covered, and they are, for instance, that this scenario is not as complex as usually is for a company. In Arcadian IoT, we are also working with some 5G and next generation network topologies. So this solution should be reliable also for those kind of network topology. And also in case of the topology changes, as it usually does in the next generation networks, because of the different edges, the different antennas that are connecting and new users connecting to our network and so on, we need to be reliable to protect all the infrastructure from the malicious attack and be independent of the topology. Also, if we are always using the human resources to act with them and to enforce some mitigation policies, and they need to be always aware with different notifications and so on to apply those policies. Maybe for a simple network like this, it works. But when the picture grows, also the difficulty and the complexity of the mitigation also grows. Sorry. So, and usually it's also important to, and it's relevant to notice, is that most of the solutions, what they do is simply stop the full user traffic. And we don't want this because we're not aware if the user is a real hacker, for instance, or is a bot, like a user that has a user equipment that has been infected with a bot that is sending a malicious traffic, but it's also using some of our services. So what we want is that that user keep using our services without us being attacked. So we want to go to the fine grain, flow, malicious flow, to stop that single flow and leave the rest of legitimate flows from the user keep going, so the user won't be affected. So this is, for instance, complexity-wise, the topology. As you can see here, this is a simple 5G or next generation network topology, and now it's more difficult to imagine, well, not to imagine, but at least to count how many points of threats can we have here, how many users can be connected to the different antennas. Here we put it simple because we only use 2 different antennas. We also see different stakeholders. Those stakeholders might be, for instance, different digital service providers that they are using the same physical infrastructure. So every time that we have something different, for instance, as I said, the multiple stakeholders involved, that same feature adds more complexity to the topology, because what we want, for instance, is isolation between the different tenants, because if they are 2 different companies, they don't want to see each other, and I don't want, if I'm a company, to see the traffic from others' company, or I don't want my traffic to be seen by other companies. So that's complexity addition. Also, we have multiple network and computing technologies, because here we know that we can have in a Linux server, for instance, we have traffic control as a technology, usually to control the traffic. Also, we have different technologies like IP tables. We have virtual switches that they can be done with Linux bridges or with Open vSwitch bridges and so on. And we also want to, for instance, have the distribution of the edge computers in geographically speaking. So our complexity always grows when we think about next generation topologies and next generation network topologies. So, and finally, one of the most important things is that we want the attack to be stopped now, like as soon as possible. And we want it to be without human intervention, at least as far as it's possible. We just want the security administrator just to supervise but not to be aware that I've been receiving an attack all the night and I need to wake up at 4 a.m., for instance, to mitigate the threat, to look for the specific point or the best point to mitigate this threat, because it's also topology dependent. And we want it to be at least as automated as it can. So now, the big question, what is a self-protection loop? So why do we call it loop? We call it loop first because it begins and ends in the same part. All this loop, it usually has like 4 main steps that we see here depicted in this figure. All these 4 steps, they always start in the data plane and they end in the data plane. What is the data plane? The data plane is the wires where the data, where the flows are flowing, where the different network technologies are taking place. So what a loop does is just to detect or identify the threat in the data plane. We divided this in the data layer and the cognitive layer, just to summarize a bit. And that detection is made in this part, in the data plane. We are, as in the picture that I showed before, we are mirroring the traffic, and the sensor, a sensor is detecting that threat. Okay, so after the detection, we go to the analysis and the decision, because as we want it to be automated, we need to have like a set of rules or some policies to be applied automatically, and this is done in those 2 different steps. For instance, if in that very moment that the attack is happening, the network topology has changed, we want to be aware of that. So that analysis and decision is also taken in real time. So we want to see the changes of the topology in real time and apply the specific decision in the very moment that we need to stop this attack. And when the decision is taken, that we will see in our contribution, what do we expect as a decision for ourselves, we will return to the data plane because it's where the flow are happening. And that mitigation is being done, for instance, with the same network technology, that it can be IP tables, it can be Open vSwitch. Regarding to Arcadian project, we will be using Open vSwitch, just to spoil you a bit. And that mitigation it can be, for instance, a drop. If we want to drop, for instance, all the traffic that's coming from a malicious flow or something like that, we can do it. But in the end, that decision, that mitigation policy, as it's thought by the analysis and decision, it doesn't have to be only a drop. It can also be, for instance, making a slice or something like that. We can just put some little bandwidth or whatever. It depends on the set of rules that we have, and we decided, for instance, for this project, to go for a drop, because we want to just drop every malicious flow that's coming from different user equipments, and just to stop it. So what we aim to achieve? What do we want with our components in the ARCADIAN-IoT framework? So what we want, first of all, is to create a self-protection loop. We want to do all of those 4 steps that I explained in the slide before, and we want first to detect and identify in real time all the threats, no matter the complexity of the network topology. And this is one of the most important things. If the topology changes right now, I need a solution with the topology we have right now in this very moment. Then to provide that fine-grained metadata information about the flow and the topology. As we saw in the big picture of the technology of the topology, with different stakeholders involved, that means that we have different network encapsulations and roles applied. So if we try to, for instance, sniff the traffic, to mirror that traffic and try to detect the traffic in different points of the network, we will see that the very same flow that's attacking us, it has different morphologies in their headers with different overlay encapsulations. So what we want is, it doesn't matter where the attack has been detected in the topology. We want to know all the technologies and all the encapsulations that malicious flow has, and where has been detected, in which of the points of the network has been detected. So in the end, we will be able to decide to provide the decisions and action to mitigate in the very best place, or at least the very best place that we think should be applied. And from our side, for instance, in a DDoS attack, another spot for you if you don't know, we are using we are simulating we are using some DDoS attacks. The best place to apply a mitigation policy, and that is a drop, should be the closest to the source possible. And we need to think all of the points where the flow has been seen, and to apply that same policy in the closest point of the network that the flow should appear. So in that case, we will protect the most part of our network. And finally, what we want with that fine-grained metadata from the flow is just to stop the single malicious flow that's incoming, and leaving the user with the rest of the experience of the service that we are providing. So now we will go a bit more technical, and we will talk about the architecture and the software components that we are using in our loop. And yes, and let's start. So here in this picture, what we can see is a high-level integration of the three main components that we are presenting in the ARCADIAN-IoT framework. For the detection part, we are using the network flow monitoring. That is the one that that you've been listening to me like a lot of months talking about. Then we have the network self-healing that will be related to the analysis and decision part. It will also have the resource inventory agent that we will talk about it more in depth later in more slides. But basically, what these subcomponents do is to tell us all the topology changes that are happening in real time in our network. So it will be this cognitive part, the decision manager, who will be thinking where is the best part to take action, how and for how long, and what action to be taken, and so on. And finally, we have the network self-protection, that it's our actuator, our mitigation policy enforcer. It's the one that receives the information that the self-healing just said with some healing instructions, that those healing instructions are basically decisions in an intent-based policy, and the network self-protection will will translate them to the technology that the network self-healing has set to apply the network policies, and it will be the one who will work directly in the data path and will stop the very one malicious flow that we want to stop, and leaving the rest of the flow free. What we are using as communication exchange is the RabbitMQ. The RabbitMQ, it's a message bus tool that we use to communicate the three components. Sorry. So in that case, they are mostly working independently, each of them, and they will be providing the different events. For instance, the flow monitoring, when it detects the attack, will provide a new IDS event that can be taken from different components, and also, for instance, to close this loop, for the network self-healing, and the same for the network healing instructions that will be taken by the self-protection loop. So then let's go deep in what the network flow monitoring is. We will go for the network flow monitoring, the self-healing, and the self-protection. And here, what we wanted to present, for instance, is that we are extending the capabilities of a traditional network IDS. We are not reinventing the wheel. What we are trying is to extend what we know that there are some gaps. Why do I say so? Because we are using, for instance, Snort as a network IDS, but there is one main gap in the traditional networks, and it's the different flow information that can be inside a single flow. Because if you try to use a traditional network IDS, it will only go for the for a particular IP. And if the complexity of the network is that huge and we have different stakeholders, we will have different overlay networks with different overlay technologies. And that means that if we only see the last of the IPs and we try to drop all the traffic incoming from that IP, what we might be doing is to stop all the attacking coming to the physical infrastructure. And we don't want that. We want to go that fine that we see the that we only stop the attack incoming from the users in this case. Okay, so that's where the security flow monitoring agent comes, because Snort is using a set of rules to match the flows that are incoming. Snort is that sensor that we saw before in the picture before, and it will write in a unified to file, is in like a log file, every threat that he has encountered. So we developed as an extension this security flow monitoring agent that it has three main subcomponents. That is first a unified to watcher. We want to be watching every event that the Snort has been doing, and then to provide information for the overlay network info recorder. So that subcomponent, what we'll do is to match the event that has been happened, that the Snort has detected, and will provide us the specific flow that is the malicious one. And in that case, it will aggregate some metrics that are needed for the self-healing in order to provide more insights and so on. And it will be pushed to the RabbitMQ as an IDS event. And this is, for instance, a JSON file that we already shared with some of you. And it's the output that this flow monitoring is using. As we can see here, for instance, we have different MAC addresses because they relate to different points on the network. We also have different IPs. We have different source IPs and different outer source IPs. That means that what we can see are the different encapsulations and the different layers in the network that the flow is happening. And then we provide some insight also about the event that we just raised. For instance, it is an alert, and the alert we know that it's fired, that we just raised the alert. This is what I was talking about. For instance, this is a picture that we can see properly here. What an IDS event from Snort is, the one that Snort writes in the unified to file. You can also write it in a JSON file, and this is the difference. For instance, this is the only IPs that Snort is seeing at the very moment. But if we see the same packet, that's the very same packet, those IPs are related only to the physical infrastructure. So that means that if to the outer IPs. So that means that if we try to stop the attack only with these IPs, we will stop the full attack. The full traffic incoming to that infrastructure. And what we want is at least to know what are the different encapsulated IPs that we have with different protocols. For instance, with virtual extensive local area network, that is VXLAN, for tenant isolation, and also the GTP protocol for user mobility. Then we go to the network self-healing. Now we move to the analysis and decision. And we can see here, we have the flow monitoring that I just discussed before, and we receive a network ADS event from the RabbitMQ. So what we have here is the picture related to the self-healing, and we can see two different subcomponents, two different main subcomponents. That one is the UWM resource inventory agent, that is the one related to the topology, and the other one is the self-healing decision manager. So we were talking about the self-healing, and we wanted to go to the resource inventory agent first. That as a summary, it's the one in charge of providing us topology, like a topology inventory, topology information about the 5G or the next generation network topology that we have here. And when we talk about topology, we are not only talking about interfaces, computers, switches, routers. We're also talking about technologies, two different technologies, because a single router can work with different technologies and can work in different network layers. And also the computers can also work with different technologies. So this subcomponent that we develop, it provides us this kind of topology information. For instance, technology related to LLDP that provides the host information, like for neighbors information, for instance, who is connected to my interfaces and so on. We have LSPCI to know the PCIs that we have. If we have different PCI with different network interfaces, maybe some with fiber or others with 10 gigabit per second or so on. We also have IP root, bridge control, Open vSwitch, list hardware, and so on. So what we want about this is to have that database of the inventory of the topology always updated. So this RIA component, what we'll do in a distributed mode, it will provide the information related to the topology that is in the moment that we have them in that moment. This is the same picture that I saw before about the alert that is raised, or the event that is raised by the flow monitoring component that is taken by the network ADS event, and it will go directly to the next subcomponent for the self-healing, that is the decision manager. That is the one that will provide us with some insights about where to take the action and what to take the action. And that's what we call prescriptive analytics. And those prescriptive analytics for us is to know what action should be taken for the event that the flow monitoring just raised, then where this action should be enforced, like knowing the very best point in the network, like the closest to source or so on, when it must be enforced, usually is right now, as soon as possible, and then for how long, if it must be, for how long should it be active or not. Like it can be like a forever drop, or we can just ban the flow for a few minutes or whatever. Then we have the mitigation actor here. That is the network self-protection. This network self-protection is another component that we have been developed like mostly full. And as you can see here, this picture is a bit different from the others because we start from top to bottom. So we can see the self-healing component, that is what it was the previous one, at the top of the network flow, the network self-protection. And this self-healing component will send the healing instructions to this self-protection network that we have distributed in different parts of the topology and will be in charge of stopping the attack. So the first subcomponent that we find here in the self-protection is the protection control agent. That is the first gray box that we can see at the top. That little gray box, it's one of the most important in this project because it's the one that receives that healing instruction and will be in charge of build the specific technology sentence like to mitigate the attack. And as we are using, as I already said, Open vSwitch, we have here the next two gray boxes are referred to. The first one, the protection decider, is referred to an extension that we made to the OpenFlow protocol. And the second one, the data path security controller, is another extension that we made for the OVS, for the Open vSwitch kernel module for Linux distributions. So the extensions that we provide for both of the OpenFlow protocol and the OVS kernel module are to be able to classify and to apply the action for the very single malicious flow that we can find, and to act through the overlay networks that we can find in a 5G or next generation topology network. And here, for instance, if you want some insights about how this works, is if we have the network interface controller here and the flow is incoming from this way, and we know that there is a malicious flow incoming from the network. The flow will go from the 5G data path, will pass the driver, and then will arrive to the Linux kernel, where it will find the 5G IoT classifier. That is another contribution that we developed. That is one part of the extensions of the OVS modules, and we'll try to match if the flow has a rule to be stopped or not. So in case if the flow is malicious and it doesn't have the rule applied yet, the kernel will raise the flow to match with the next rules of the OpenFlow protocol that are the one built from the protection control agent. And whenever it matches in the OpenFlow protocol, they will be applied to the data path. And they will be stored in these protection rules. So we won't need to go again to the OpenFlow protocol, as we will be stopping the attacks at kernel level. So it will be more efficient. This is another picture, for instance, another pickup that we take to the different insights of a very single flow that can be found in a 5G IoT network, for instance. And we can see the blue square are referring to the infrastructure traffic. Then we have the orange box related to the tenant traffic, that we can see, for instance, that they are using VXLAN as technology for isolation. Then we also have some GTP headers to identify the user. So with this information, what we can do is to provide that fine-grained metadata, or that fine-grained flow that we just want to stop. Here it's more or less talking about the same as I said before, that if a single flow is detected in different parts of the network, it can have different encapsulation layers. So maybe what we can see is only these encapsulations for the original IoT device traffic. But if we go for for the tenant, we can see more IPs and more flow information. And when we differentiate also about the physical infrastructure, we can see also this yellow. That means that the three steps are related to the same malicious flow. They relate to the same malicious flow, but we want to be as specific as possible to stop as we said before, as we are saying every time, to stop the specific malicious flow that we want to stop. This is the picture of the architecture of the 5G IoT classifier that the self-protection has. Is that little blue box that I saw in the picture before. That is one of our contributions. And what it is, it's a network parser that it helps it will help the OVS kernel module that we extended to have all the information all the overlay information that's happening through the flow that is being detected by the classifier. So it will provide us information as of all of the layers that we are using, and also additional information about the tunneling protocols that flow has been detected in that specific part. So now I will put some example and like a real scenario of the threat detection, the planning, and the mitigation of this one. I will try to go a bit fast because I think I don't know how much time I have left, but we will come back. We come back to this picture. For instance, is the 5G infrastructure that I showed you before, and is the one that we used for the demo and for the demo in the last review meeting. And what we can see here are different network segments of the 5G network. For instance, we could say that the run of the network is here with the user, the distributed units, and so on. We have the edge of the network, and then also the compute network. And in this specific scenario, what we want is to show how these users that we have here that are connected to our premises, some of them will be infected and some of them won't. And all of them are using the RGB servers that we also used in the demo, and they are the medical IoT devices that were connected to that server. So what they want is at least to have to still have the service of the medical service and not to attack our infrastructure. So what will happen is that the normal flow will be this one. We will have some flows incoming from the UEs, and we want to go to the web server, for instance, of the RGB, where they are consuming and posting their health metrics and so on. And we can see that if we have different tenants, they will have different paths. We don't want the traffic to mix between the different stakeholders in the network. So if we have traffic isolated from tenant A to tenant B, what we use, for instance, is VXLAN. That's why we have the virtual switches here that are the ones related to isolate that traffic. Then we have here this physical switch that we have here. We are using, as I saw in a picture before, a mirroring to another compute that is the one in charge of the management of the networks and protection loop. So that mirror traffic will be incoming to that physical compute, and it will find the first of our component that it is the network flow monitoring. So the network flow monitoring will know if the traffic that's incoming to the core of the network is malicious or not. It will match with the rules, and it will raise an alert if, I think, yes, it will raise an alert. But we will go there, because what we see here now is that some of the devices have been infected, and now they are going to start attacking our premises. And that attack, for instance, can be a DDoS attack. In this case, it was a DDoS attack, and we found that we couldn't manage the bandwidth, like the low bandwidth that we were having because of that DDoS attack. So what we want to do is to stop the red lines. We want just to have the blue lines here. So what will happen is that mirror traffic will be detected by the network flow monitoring, and it will send an event to the self-healing decision manager. And that self-healing decision manager will receive that same event. And as we have, I didn't say it before, but we have here in the different physical devices, we have the RIA component, that is the subcomponent of the self-healing, that is always providing us information about the topology. So, and this information is already taken by the self-healing decision manager, yes, will be able to do the prescriptive analytics and provide us the specific location and to mitigate the threat. And in that moment, it will send that self-healing instruction that is a set of intents related to the where, what, when, and for how long. and it will provide it to the network self-protection component that, as you see, is distributed in the different physical machines to stop the attack. In this case, why do I have an arrow to this self-protection loop and not to the other self-protection loop that we have here? Because our policy was to stop the attack as close as possible to the source of the attack. So this is the best point to for us to stop the attack in this edge computer. So what we'll do, the self-protection is to receive that self-healing instruction, and then in the data plane, as we are using Open vSwitch and the extensions that we made for the Open vSwitch, it's enforcing the rules in the interfaces of the virtual switches that we are using in the infrastructures. So what we'll do is to apply that mitigation in that very of the network. And what we will see is that now we could stop, at least in the most part of our topology, the attack. And now we still have the service that are the blue lines for the UVs. We cannot go deeper to the user equipment right now because we are focusing on the network side. So that's why we still have we are not aware if the devices are still infected or not. We just want to stop the attack at that very part and protect our premises and so on. I don't know how much time I have left, but I have also the demo here, but it's the same demo that we already saw in the review meeting. So we can go on and not showing it, or
it's good to show it.
It's good to show? Okay, perfect. So I don't know if I can do this and it will open. See? Okay. Okay. Again, this is the demo. Okay, no, it's not showing. Sorry, it's not showing the presentation because it's in another app. Oops, sorry. Sorry, you go. I think maybe it's because it's in another. What if
it's on the Zoom, I think.
It's on the Zoom?
Yeah.
Yeah, but we cannot see it here. How can I? Okay, I will do something. I will close the presentation.
Mm-hmm.
And now, yes, perfect. So, this is the same scenario as I described before. What we were using here in this demo are the RGB servers for also partners from ARCADIAN-IoT, and also the SIMs for TruePhone. And here, for instance, is our testbed scenario that we have in our premises in UWS, and we prepare different switches and different computers to act as the different segments of the 5G IoT network. And also we have, as you see there, the management layer. All of them are connected by this transport network, and we have a last computer here that is the emulator of the medical IoT devices. But we also are using the proper IoT devices and some antennas. But as we didn't have as many IoT devices, we emulated the rest of them. And what we can see right now is, for instance, how we were using the true phone SIM that we were inserting in the smartphone. And here we were using the different medical IoT devices and connected to the servers. And now we are logged into the servers and we are sending the metrics to the RGB servers. And those devices are connected to our colleague, for instance, here, and we were sending those metrics. Here is where the magic happens. There are two different graphical interfaces that we developed to see the behavior of the network self-protection loop. In the left side, what we will see are the different RabbitMQ publishes that we will be facing. For instance, when the flow monitoring will raise an alert, and when the self-healing will raise a decision, and when the mitigation will enforce an action, and so on. What we can see in the right side, there are different bandwidth monitorings differentiating. We will see now the different flows from the attack and the legitimate traffic. And what we have at the bottom of the screen, we cannot read it really good, but then we will do some zoom, are like the control plane where we start the experiment, and then we also are monitoring, for instance, the Open vSwitch rules that will appear at the moment that we stop the attack. And here we can see, for instance, in the left side, we have the legitimate traffic, and in the right side, the malicious traffic, and also what each of the console are related to. These are the infected user equipment, and those are the rules. Now we start the attack, and what we can see is how we are already receiving traffic. We can see the uplink and the downlink traffic for the RGB server. We are only in this very part. We are only using the legitimate traffic right now. And now we can see that we have some bandwidth, that the UEs are connected and some flows are happening. And now we start the attack. And as we can see, at the very moment, some of the flow monitoring alerts have been raised, and we can see that the RGB servers are having like some disruptions of the in the bandwidth, and we see like the DDoS attack going like for top. And now the self-healing decision manager, we needed to put it like so slow because it happened too quick. And this is the zoom of the top console that we can see here, the different applied rules at the different mitigation rules that were happening, and then we can see the legitimate traffic was continuing happening while the attack was being stopped. So, and this is basically the last part. Okay, so that was the demo. And finally, okay, now I think I lost again the no aquí here. Well, first I think I need to do this. Okay, now? No? Okay, perfect. Okay, so that was our demo. And now we will talk a bit about the contributions that we made. We could present a conference paper in the IEEE protocol conference of network protocols in Reykjavik that we will be presenting in this next October. And what we can see here are the different consume times that we decided to experiment with our network self-protection loop. And what we can see here is that all like the different colors of these graphics represent the different times that the components of the network self-protection loop were taken. And also we have a split here between scenario A and B because we were changing the topology. We wanted to be independent from the topology. So in the scenario A, we have like a more simple 5G IoT topology with only two different physical edges, and then the core and the rest of antennas and so on. And we have up to 64 infected IoT devices. And in the scenario B, we made it more complex, adding more topology resources. And what we could see is that there are different components that are working much better in distributed mode than in centralized one. And for instance, if you want to know the why and how did we manage to emulate all of those infrastructures, we were using core emulator to provide those topology. This is a picture that I took from the core emulator, and it represents the connection from the UEs, from the radio access networks to the antennas, and then going to the different physical infrastructures. So this is basically like a translation from the different pictures that we saw before, but to the emulator itself. So what we can see is that like how the UEs are connected to the edge premises, that we have the purple boxes. They are different tenants. So we also wanted to play with that tenant isolation, and then they go to the core premises where they also have different tenants and so on. And the attacks were happening to those server victims that are in the seventh bullet point that might be in the demo before, for instance, the RGB servers. So this is everything from my side. I hope it was not so boring. So thank you very much to all. And if you have any further questions, please go on. Yes?
Cool, nice presentation. I liked the clip, the music.
Yeah.
How do you do the detection? How do you realize if some kind of packets are actually related to some malicious traffic?
Okay, may I go to a previous slide if you allow me? So I will explain it better with a slide. Here, to the flow monitoring. The flow monitoring is the component from our side that is detecting the attacks. Okay, so what we face are known attacks. What does it mean? That means that we already have a rule. We have a set of rules that if we match from the data plane, the snort matches one of the flows, we'll say, okay, this is a threat. It can be an attack, it can be whatever thing. In this case, our rules are based for DDoS attacks. So when a flow is coming here, the snort is reading in that mirror traffic, it will see that it relates, it matches with one of those rules, and in that very moment, it will write the alert in the Unity file, log file, and it will be the security flow monitoring agent who will be expecting some changes in that log file, and will then extract the overlay information for the rest of the flow. So we will have the full malicious flow. So the flow monitoring, the only thing that it's raising are malicious flow. Well, not malicious flow, the flows that might match with the rules that we have here. If we set up a set of rules that are for malicious flows, we will only match malicious flows. If we want to match, for instance, TCP traffic, we can prepare a rule for that TCP traffic, and Snort will write in all the TCP traffic to the log file. So basically, how we do this detection of the malicious flow is using the traditional network IDS, but as I said before, we extended with the security flow monitoring agent to provide more information about the flow itself of the overlay networks and so on. I don't know if that solves the question.
Perfect. So I suppose this will work great at, up to the TCP level, like level 4, whatever it is, but then application level, so that I've got, a case of session hijacking.
Yes.
You wouldn't be inspecting application traffic, right? Because then you'd have to know the way these applications work. Or are you expecting, for example, big traffic?
At least from UWS, we only work at network level. We don't want to go to the application layer. So we are only focusing on the first 3 to 4 layers, more or less. Right. So every attack that is in the 7th layer or so on, we won't carry it. Like we won't be able to stop it. We are only focusing on the network part. So
thanks.
Thanks to you.
The mitigation rules.
Yes.
How are they decided? Human decision or is it automatic?
Okay, let me go for another slide. Okay, because maybe I went too fast in some. Yes, I think this is the one. Okay. No, sorry. I will go for this one. Better. It's the same one, but bigger. Okay, so we see better. Is it human decided? Yes. Why? Because we have the healing decision rules there that they work more or less as the rules that we have in the detection part. So what we do is, depending on the topology at that very moment and the rules that we would want to apply for the different attacks that the network flow monitoring should raise, like, okay, we are having a DDoS attack, or we are having a brute force attack, or we are having whatever kind of attack. As we expect to work with those known attacks, we prepare some healing decision rules, and those rules are related to if we want them to be close to source, or maybe close to a destination, because it depends on the attack. It's not the same, for instance, if we have a DDoS, we want to be at the closest to the source, because in that case, we will be like fulfilling all the network interfaces of all the infrastructure and so on. So the rules are predefined by us, and it will be the self-healing decision manager who will think with the topology in that very moment, where and what is the best action plan to take in that moment. But those rules are predefined by us.
So the system only defends against known attacks?
Yes.
New ones?
If the point with, for instance, Snort is that you can defend yourself for new attacks, yes, but you need to update your rules. If you update your rules, you get access to new attacks that have been happening. But what we wanted to differentiate between known and unknown attack is that a known attack is an attack that we have a rule for. It's not an attack that we know that have been happening these years or whatever, but for us, if it's not in our rules database, it's an unknown attack. So we only apply for the rules that we have. For us, those are the known attacks. I don't know if that solves the question or.
One last question. Your work is with healthcare, like it's quite generic.
Yes, because we were.
Communication.
Yes, because we were working, as I said before, in the network part of the project, and our contribution was for that network part. As other partners in the IoT framework were more related, for instance, as TruePhone or RGB, they were facing more in the medical servers and the medical IoT devices, and so on. And we were providing some capabilities for the network infrastructure to be protected. So that was our plan, and is our plan.